So Bohr, sometimes what happens is somebody will have a model and then it gets replaced like years after they've died. That wasn't the case here. Bohr's model was great, but then he himself realized, okay, wait a minute, it's not working for other things. And this is the same time in the early 20th century when people in physics and other disciplines were starting to discover quantum mechanics. And so that became, they turned to quantum mechanics to see if that would help explain what's going on with the atom. And it actually does. This is very revolutionary because until this point, electrons were thought of solely as particles. And that's how I've presented them to you. They're little tiny particles. They're smaller than the proton and the neutron, but they're these little particles. Well, it turns out that electrons do not always behave like particles. Sometimes they behave like waves. Light, we think of as a wave, but it can sometimes act like a particle. Electrons can also behave as both. So in quantum mechanics, we replace orbits with orbitals. And they're kind of similar, and yet they're radically different also. An orbital is a probability map that shows a statistical distribution of where the electron is likely to be found. And that's a very simplistic explanation, but trust me, you don't want any further. So I think of this as a little bit, you know, I like to personify things, and I have this crazy place I call chemistry land. And so electrons remind me of little boys, especially my son Andrew. He's 6 now, so he's not quite as crazy. But let's pretend that this is my house. And here's the couch, and there's the TV, and there's my bed, and here's his bed. And then there's the kitchen table with the chairs. There's lots of chairs because there's lots of people. So where's Andrew? Well, on the couch is a good bet. Yeah, here, Andrew's family color is orange, so I'm going to give him orange here. So, snapshot of the house, there's Andrew. 5 minutes later, there's Andrew. Okay? Oh, he went to the kitchen and got something to eat. Oh, he went over here. He sat at the table, then he decided, nope, I'm going to eat on the couch. Oh, I'm going to roll around on the floor. And so you get this, you know, oh, got to go to the bathroom. Where's the bathroom? He's going to use my bathroom. You get this idea, oh, he's going to go outside. Oh, he stole the neighbor's big wheel and went to his uncle's house. That happened when he was 2 years old. Who does that? This person. It's a good thing he's cute. Anyway, after a while, you'd get this pattern of where Andrew is likely to be. Can you predict where he is right now? No, you can't. But could you make a statistical probability map of where he is? You could. That's what an orbital does for an electron. We can't say it's right here and this is what it's doing. But we can say this is the region of space where it probably is. Because you can't even predict if Andrew is going to be on our property, right? He may have gone for a walk by himself. You just never know. And that's the way electrons are. They're very squirrely. Okay? So there's my analogy of orbitals. Yeah. So let's think about baseballs versus electrons. So here we have the pitcher pitching a baseball. And they have pitching machines, right? You put a ball in a pitching machine, and it does the same thing to the baseball, and the baseball goes in the same place every time, right? This is understandable to us. It's called determinacy. It's what is happening right now to something predicts where it's going to be in the future. This is how things that are large enough that we can see behave. You throw your cell phone across the room, you can kind of predict what's going to happen, right? So that's not how electrons act. Electrons are extremely small. And when you get down to the extremely small, the rules don't apply anymore. Just like for Andrew, the rules, you can't leave the property without telling me where you're going, doesn't apply because he just ignores it. So if you threw an electron exactly the same way, like the pitcher is throwing the ball, it would land in a different place every time. I find that very disturbing. Einstein didn't like it either. So if you don't like that, you're in good company. This is because electrons and photons, those packets of light, exhibit wave-particle duality. They act like a wave, and they act like a particle, and they can do that at the same time. It's called superposition. So the best we could do if we were pitching electrons, pitch an electron exactly the same way each time, this would be, all these little dots are where the electron hit. So we could predict, well, 20% of the time it was in here, 40% it was within this radius, 70% it was within this radius. But you know, sometimes it may have gone and hit this guy right between the eyes, right? It might have actually gone the opposite direction. I threw it towards home base, but it actually went towards second base. Doesn't have to make sense. It's just what electrons do. Any questions? So the word orbit and the word orbital are very similar. Try not to get them confused. An orbit is like a planetary orbit. It's a circular elliptical path around the nucleus, and you can predict. The electron is in the orbit. I know it was here at this time, and it was traveling in that direction with this speed. I can predict in 5 minutes where it's going to be. But electrons don't behave like that. An orbital is like a time multiple exposure photograph of where the electron is at any given time. And this is how an electron can go from one state to another, from one orbital to another, without being in between, because it can actually be in two places at the same time as a wave. Completely unpredictable. Okay, how can waves be in two places at the same time? Let me show you a video.